Okay, thank you, and thank you, Federico. Good afternoon, everybody. As Federico said, I'm Neil Spahn. I'm CEO of Powerroll, and I'm delighted to have the opportunity to tell you about our revolutionary way to harness the energy of the sun. So what is our mission at Powerroll? We're wanting to power a rooftop revolution of solar power via a disruptively low-cost, lightweight, and flexible solar solution, and actually to create opportunities to generate energy from virtually any surface around the world, and we'll talk about that later. And we can do that through our unique and patented approach to making our solar film. So I've got a short video that I'd like to play.
We have created a completely new way to generate solar power. Our technology uses microstructures smaller than a human hair etched into a flexible plastic film. It is simple and low cost to install. Ultra thin, lightweight and extremely durable, our technology allows us to generate solar energy anywhere and everywhere, using any surface. Installing solar power in more workplaces, homes and transport will enable new markets. Our technology is proven and patented in over 50 countries, making flexible, low-cost solar power available to all. Limitless shapes and sizes enable a huge range of products and applications. As the planet seeks new energy solutions, Powerroll has created a new way to generate solar power, offering the lowest possible cost of electricity in a scalable, sustainable, and proven technology.
So let me tell you a little bit more about this, and we'll get into the technology in due course. So this is a technology that's developed here in the UK, actually in the northeast of England, not in County Durham, and it is potentially game-changing in the solar sector. We're able to generate energy from those surfaces where you cannot currently generate energy. And we'll talk about this in a minute, but the easiest way is to look up at the roof where we're sitting in the building of. You're not going to put the heavy traditional solar panels on this. This is a perfect roof as a smaller example of what we're trying to do here. And it opens up something like 12 billion square meters of surface to generate energy. Where are we with the business? We've got a pilot plant up in the northeast, and we're looking to build our first commercial scale factory next year to generate over 1 million square meters of our film to power schools, hospitals, and businesses going forward. And then our plan is to expand that plant and license this technology globally. So let's just stand back a bit, and hopefully by the end of this presentation, you might be a bit of a surface nerd like me. And you stand back and say, you look at all the surfaces, the building of this, if you're on the train, have a look at the warehouses that you're passing, if you're in a toll. Why, if silicon PV is so good, why is it not on every rooftop and surface? Okay? Less than 2% of all the rooftops around the world have PV on them. That is crazy. We've just heard the presentation from the Net Zero Minister this morning, talked about increasing the UK solar by 50 gigawatts, 5 times where we are today. And in the Times this morning, there's a 10 gigawatt backlog for solar farms because we can't get grid connections sorted out. So let's use the buildings and surfaces that we've got here. And what we need is we need something that's better. We need something that's lighter, it's more flexible, it's easy to deploy, and importantly, it is more cost-effective to unlock that solar rooftop revolution. And really, our technology we'll come on to now is to drive down that cost of adoption. The small picture here is the Team Valley, which is up in the northeast, which is was one of the first and one of the largest industrial estates. You'll actually see the amount of deployment there of PV is very, very low. And it is increasing. I think your next presenter is going to talk about that. It is increasing. But there are billions of square meters that cannot be addressed from what we've got today. So let's just talk about that. Less than 2%. So silicon, it's heavy and rigid. So obviously where you have load limiting issues, that's a prohibitive factor. There can be issues with shading and partial shading of those surfaces. Building solar, so let's just talk about the elephant in the room. We're importing 95% of our solar panels from China, probably 99% quite frankly. That is not a brilliant business model for UK PLC, so why not create some manufacturing here where we can actually be self-sufficient for our solar panels? And the issue with why are there no silicon factories in the UK? It is highly capital intensive to build a silicon factory. Probably $250 million plus for a gigafactory. Ours is an order of magnitude less. And also it's very labor and energy intensive, which our technology isn't. There are flexible PV solutions out there. You may say, I've seen this before. You really haven't. But they are inherently expensive because they use the same technology behind silicon PV. A little bit about our tech. So what we do is we turn the solar cell on its side to create microstructures smaller than human hair. It gets rid of a number of the process steps used by others. So, for example, the expensive ITO layer, for those who are technically minded. We don't have to have any cell and module connections. They're all done. It serves no rare earth materials, no indium, no gallium. It's very low cost and easy to scale. We actually use the same processes as you would use to print a banknote. And we'll talk about that in a second. This technology is patented all around the world. We must update our video. We've got now over 100 granted patent rights in over 70 countries now. And importantly, again, no one talks about the built-in carbon. There's a lot of energy, there's a lot of power goes into making silicon panels. Ours is 20 times less because it's low temperature, it's high speed, and we don't require some of the complex processes that others use. So our payback is as short as 40 days from a carbon perspective. So let's talk about our process. So we start with standard plastic, and into that we emboss our unique microstructures. So in what I'm holding in my hand, which is a tiny sample from our pilot plant, there are over 100,000 solar cells connected into 400 modules. It's completely unique technology. We then take it through three other process steps used in high-speed industries, and we end up with a roll of film, which I've got in my hand here, which is lightweight, it's low cost, it's easy to deploy. The capital cost to build the factories is an order of magnitude less, and as we said before, no rare earths, abundant materials, and heavily patented technology. A little bit difficult to see on the slide there, but anything that's not grey, we have patent protection. So either pending or granted. We've got 22 patent families all over the world, Europe, Asia, US, and certain parts of Africa, because this is a technology that will go all over the world. We've won various awards over our time. We've just been over in the UAE with the UK government, looking at sort of clean tech disruptors. And you know, this technology is widely recognized as a leader in the field. And we seem to have lost the slides. So I will wrap up and we're back. So let's just quickly talk about the economics. So basically, when fully scaled and manufactured, the potential for our solar roll is to be 3 times cheaper than the panels made in China and up to 5 to 10 times cheaper than existing flexible PV. And that's the disruptive factor. That's what gets us excited. And if you're going to install this on a roof in the UK, your payback period can be as short as 3 years. And the IRRs are fundamentally exciting. A little bit of UK I mentioned before. We want to put in 50 gigawatts. We're importing all our panels from China. We can make them here. We can open up those rooftops where traditional PV can't go. And basically, we can use the land for other purposes. And there's some great use cases that I'll not get into today. But here's some of them. So as well as commercial buildings, we'll take this off-grid. So powering homes, communities, hospitals in India, Africa, Southeast Asia, onto architectural fabrics, the Millennium Dome, and many others that look like that, agri-tech, and commercial transport. Putting this on the tops of trucks, the sides of trucks, to power the air conditioning and other electronics in there. You're not going to power the truck, but we can absolutely bring down the requirements for those systems. So where are we in our story? And I'll wrap up here. So we've proven the technology. We built a pilot line up in the northeast where we can make hundreds of meters of our film. We've got some, that will be completed by the early autumn. We're going to be raising the funding to build the first factory, ideally in the northeast of England. We've got a few sites we're investigating. And then basically we're looking at scaling that up and then going for that giga growth across the world through a licensing model. So I'd love you to come and see us. We're on stand B12, just in the top right-hand corner, and join us on our solar revolution journey.
Thank you, Neil, for your presentation. Are there any questions from the audience? One here.
what is your output? Is it per square meter? What is the voltage or and current?
Yeah. So if we look at it at a power perspective, so once we finish the pilot line optimization, we'll be about 100 watts a square meter. What's pretty interesting, and I'll not bore you with a long technical explanation, in the same surface area, this one happens to be 300 volts. It could be 500 volts, it could be 40 volts, because we can arrange our microstructures in essentially any pattern that's required. So, and then the journey then is to increase the efficiency further. Our main driver as power role is to bring the cost of adoption down. And that journey of increasing efficiency from 100 watts a square meter, or 10% efficiency, as people would extend, up towards 16 and higher is what we'll be progressing in the future. But it's making the cost affordable to all.
One question. The other hand.
I'm not sure whether I have missed it. You mentioned something about efficiency.
Yeah.
So I'll ask a question about the efficiency, and also at what conditions the efficiency were measured. And secondly, I wanted to ask about the stability. What's the longevity of the system?
Yeah. Great question. So as I just answered the previous question, might not come across in the microphone. So we'll be at around about 10% module efficiency. So obviously it's less than silicon, absolutely. But in the real world, the benefits of our technology, there's two interesting, but because we've got each of our modules is essentially microscopic. So in here, there's about 400 modules. So if I punch a hole through this, genuinely, drop a brick on it, cover it in dust, we only lose the tiny amount of that module that is lost. We don't start to impact other cells and modules, etc. And in terms of durability, we're aiming for a lifetime of around 15 years. And then you would replace it with another film. Interestingly enough, if the payback period is 3 years, take it overseas, it could be as short as 2 years or 18 months, then you can replace it. And we were putting solar panels on the roof in the UK 10 years ago. Efficiency was about 2/3 of what it is today. So technology moves on, but those are the... Okay.
What is the stability?
Yes, so we're doing a lot of testing on that. We've had some of these panels out now for a year, and the performance has moved by literally nothing. So the stability is very good. But again, we're being a little conservative on lifetime. We're not going to promise 25 years. We're not going to promise... So we believe we're trying to be a little more conservative and looking at that sort of around about 15-year life.
What sort of degradation in performance do you get as the temperatures go above 35, 40 degrees Celsius?
Yeah, so that's a great question. So this is where the nominal efficiency versus real life efficiency. So here in the UK, less of an issue, but the temperature coefficient of the materials we're using are better than silicon. So what you'll see is as silicon heats up, its performance comes off a bit, for sure, and ours will come off less. So that gap between 10% maybe for PV, for us, and 20% starts to narrow. So it's a lower temperature coefficient. But what I would say is silicon isn't really our comparator, because essentially we want to go everywhere where silicon can't, if that helps.
Hi. What do you think would be the capacity needed to bring down the cost of production to the level that is as competitive as silicon?
So the only limit, because again, the equipment we use is widely used in the holographic sector, banknote printing, etc. So the limitation is not in equipment. It's not going to be in availability of space, because a gigafactory for us requires about 100,000 square feet. So the main limiting factor will be speed of capital into the business, fundamentally. So in terms of building those gigafactories and the adoption therein. So there really isn't many limiting factors, because the materials we're using aren't limited, the processes are known. So we genuinely believe by 2030, and that there will be approximately 30 gigawatts of licensed potential. We already have early stage partners in Japan, India, and Europe who want to set up factories, but of course they want to see the UK factory first. So access to capital and speed of that will probably be our limiting factor. In terms of roof space and surfaces, we're never going to make enough to keep up with the surfaces that are out there, if that makes sense.
There are other questions, but we have to wrap it up, unfortunately. Maybe they can meet you at a stand or...
Yes, come over to B12 and we'll answer all your questions for sure.
Very, very good. Thank you very much for your presentation. Thanks for attending. We have a 5-minute break right now, and then we're going to talk about solar's dirty little secret.